Thank you, everybody. Thanks for coming in and joining this session. This is a Spark SQL session. Specifically, we're going to look at Spark SQL performance tuning and how you can really tune your apps to perform better and utilize the machine resources better, and in the context of Synapse Analytics. I am Ajit Ramanath. I'm a Senior Cloud Solutions Architect at Microsoft UK. And let's get on. Agenda. Firstly, we're going to have a look at Azure Synapse, the architecture. And a lot of you probably were in the other sessions where Synapse was, was introduced. And there are three main big data services or components that can do big data within Synapse Analytics. So there is the SQL pools, there is Spark, and then there is ADX. So we're going to look at that, and we're going to double-click on Spark and Spark SQL for this session. And bulk of the time will be spent on explaining the factors that affect performance of Spark SQL queries and applications. And the other thing we're going to do is a quiz called Help the Hedgehog. So all you have to do as audience is there will be questions, and you have to help answer that and then help Sonic move to stop 1, 2, 3, and then reach his goal, basically. So yeah, so every time you give a right answer, he'll move one step. So please pay attention. And yeah, let's get this going. All right, Synapse architecture. So on the left-hand side of this slide, you would see all the different data sources. It could be on premises, it could be on cloud, or SaaS data, streaming data, and so on. Synapse has tools within it to ingest those sorts of data sets. And then on the right-hand side, you have different services that you could integrate it with. So you have Power BI, Azure Machine Learning, data share, and so on. And also a governance service called as Azure Purview. So that is to provide you with the cataloging and capabilities like lineage and so on and so forth. Within Synapse, going from bottom to the top, so you have a decouple architecture there. So you have the data being ingested into data lake storage, ADLS, Gen 2, and then you have the analytics runtimes over there, SQL, Spark, and ADX, as I said. And the rest of it is basically the user interface, like notebooks, SQL scripts, and so on, data flows, pipelines with ADF components are all built into the Synapse service, and then REST APIs and SDK through which you could interact with the service. The focus of today's talk, as I said, is going to be Spark, and more specifically, it's going to be Spark SQL. So what is Spark? So how many of you are familiar with Spark? Quick raise of hands. Do you use it regularly? OK, OK. And do you use this for analytical queries or ETL pipelines or machine learning and things like that? So you're familiar with that? OK. So Synapse has Spark, and then, of course, this is open source Apache Spark that it provides. And the four main subcomponents over there: Synapse ML for machine learning, streaming for all the real-time analytics use cases, SQL for batch and interactive queries, and then GraphX is mostly for graph processing. The most important piece, behind the scenes, what happens is the stuff that happens behind the scenes is with the Spark core, where it provides different language runtimes, Python, Scala, and Java. Most important, widely used. Python is mostly the most used language runtime, and then you have R, which is in preview in Synapse. The focus, as I said, is going to be Spark SQL for this talk. Right. One more introduction slide, and we'll jump straight into the Spark SQL performance tuning. The Spark architecture, so these are important concepts, so just a refresher. So Spark has a driver and executor architecture. So you'd see the driver node on the right-hand side, where you have the, this is the driver node, and then you have the Spark context in the driver process. The driver process runs within the driver node. And then you have the worker nodes, which can scale to hundreds or thousands. And one of my customers has a 1,000-node Spark cluster, processing tons and tons of data. Think about things like machine data, IoT, or clickstream data, weblogs, and so on and so forth. So it's a lot of data set that they want to process. So it can scale up to thousands of nodes, thousands of workers. And then the beauty of this is that it does the divide and conquer, MapReduce, but does that in memory. So that is the most important distinguishing factor between Spark and Hadoop. Although Hadoop also does MapReduce, but Spark does it in memory. Now, all those slots that you see at the bottom here on the worker nodes are basically containers or slots, or they're basically executors. So you have a task, you have a certain portion of data that you want analyzed, processed. The executors will pick it up and will run it. So that's basically what is the architecture. And the most important thing for this talk is also the point about the network over there. So the communication between the different nodes is over the network. So something to bear in mind. I'll tell you why later on. And then Spark also has various connectors. Needless to say, I think you can connect to the cloud storage, RDBMS, and so on. And the other thing to notice here is also what is Spark what is an operation within Spark. So there is it has two parts to it. One is the transformations, and then there is the action. So what is a transformation? Transformation are things like filters, or you're basically doing a map operation or a filter operation. You're doing some, let's say, a join operation and so on. So you define all these different transformations that you want to do on your data set, and then you run some actions such as writing that to a table, or maybe collecting that data and so on, which is the action. So until the action statement is not seen or not sent to the engine, it doesn't take any action. So it's basically lazily evaluated, right? So the transformations, just running the transformations doesn't mean anything in Spark. Right, so quiz time, first quiz. So Azure Synapse Spark can read files from Data Lake, Azure Data Lake, true or false? True. Yay. That was an easy one, good stuff. So stop number 1 for Sonic. Now, let's open it up a little bit. So what is a driver and executor, right? So driver process, what is it responsible for, and what is the executor responsible for? So the driver translates the user program into an execution graph. So what do you mean by execution graph? So people familiar with, let's say, regular SQL, do you understand that there is something called as, let's say a query plan that is built by the engine? So something like that. So think about it like an execution graph is a query plan, and then there is also, it's also about, it's not just about the graph, but also having a physical plan of who's going to do what, and the splitting of the graph into different stages, and so on and so forth. So those are activities that happens first when you submit the program. The driver takes responsibility for that, and then it also runs things like collect, show, and so on. Those are action statements, referring to the previous slide, it's transformation and action, and then things like 2 pandas. I don't know if you guys have used Python pandas, anyone? Yeah? Okay, so this is single-threaded, right? So Spark is multi-threaded. In a sense, it is a distributed computing platform, right? Whereas if you bring your data frames or data sets into pandas, then it becomes a single-threaded operation. So that runs typically inside the driver. So something to bear in mind, especially given that we're going to talk about performance. Executor is basically lightweight threads, workers that runs the tasks that the app wants it to run. And it processes a certain portion of the data that is assigned to itself, right? So that's basically what executor does. And and then it also takes the responsibility of outputting that to the external database or data lake or wherever you want to write it to, right? And it caches as well, so you can run a cache of a data frame or an RDD. I'll come to what a data frame and an RDD is later on, but that basically spills to disk as needed. Right. So just a refresher again, what is MapReduce? So MapReduce, now think about this whole thing, the whole operation left to right is happening in memory, right, in Spark. So firstly, you have, what we are doing here is a word count, a simple word count. You have simple words like SQL DW, SQL SSIS, and things like that, which I'm hoping you guys are familiar with. So just random words. And what's happening here is you're submitting this as the input to the Spark engine, to your program. Spark will then split it into, this is called as a partition, basically. So it splits into multiple partitions, assigns it to, these are tasks that happen on top of that, so map operations that happen on it. So these are executed by individual executors, which is what I mentioned as a driver and executor. So the executor will take up that job of counting in its partition how many occurrences of SQL, how many occurrences of DW, and how many occurrences of SQL again. So it's basically each task is running how many counts it can find in its partition, basically, right? So that's the map operation. And then there is a combine operation. So you can also then think about the executor as combining it to say, OK, in my partition, I have SQL so many instances, but then, it's basically going into each of those different keys and saying this key appears twice and another key appears 3 times and so on and so forth. So combine happens here. And then if you notice, the reduce operation is required to then basically collect everything together and sort of give a final count of how many times that word was repeated or how many times it appeared in the input document, right? So the reduce operation before that, each of these keys are assigned to individual partitions, which we call as shuffle partitions. So the shuffle partitions, basically, the number of shuffle partitions determines how many different executors are going to execute on that reduce step, basically, right? So then what's happening is each of these keys, in this particular case, if you take SQL, so this partition takes responsibility of SQL. So SQL is the key, and then it gets the numbers from each of those mapper jobs. So the shuffle is basically shuffling the counts and bringing it into one shuffle partition such that a count can happen on it. Okay? So this is basically map and reduce, and then finally the output after the reduce is to give the final word count, right? So this is how Hadoop has operated. Very similarly, Spark is doing it, but then in memory and a lot more optimization that has gone into it. Quiz time. So use of pandas data frame in Spark results in single-threaded. I answered this. So what's the answer? Right. Yay. OK. That animation was quite slow. Moving forward. OK, so what are the factors affecting performance of your Spark application, or Spark query? So I've split this into three things, 3 important items. So one is the Spark pool configuration, which is basically the machine on which you're running that application. Number 2 is user queries. So how have you written your query? And what are the configurations that you've added to that query? And then lastly, what are the different formats, file formats, and storage? So it's basic housekeeping as well, isn't it? So you want to make sure that you have structured your table in such a way that it is efficient to read and write to it, right? So that's basically the focus of this talk. Spark pool configuration is very, very important first step. So where you're going to execute your Spark query. So Spark SQL query is going to be executed in Synapse in a Spark pool. So I'm not going to go into a demo of how you can set up the Spark pool. That's there in Synapse documentation, so you can go and explore it. So once you come to the section where you have to define the number of nodes and set certain properties, that's where this screenshot is going to help you. So number 1 is the node size. So firstly, you can choose between small, medium, large, sort of t-shirt sizing, right? So you can go with a medium 8-core 64 or a small 4-core 32 gigabyte and so on. So you can define the node size. And from a performance point of view, auto-scaling plays a very important role. So this, when you enable it, so you don't go with a static set of number of nodes. You can go and set it to elastic. In a sense, you can start with a minimum of 3 virtual machines and scale it up all the way to 10. And the machines are scaled up and down, and it's elastic between these two numbers, 3 and 10. So the system, the service takes care of it, so you don't have to really, it's basically you set it and then you forget about it. So you run your programs, and then it'll scale up and down as needed. And then there is something called as dynamic allocation of resources, which is also an important thing. So you can enable it over there, or as a session within your notebook or your application, you can set how many executors you want to run. So imagine a cluster where you could have, let's say, you have 3 machines to start with, right? That's your base over here. And these 3 machines, let's say, have a combined strength of 64 times 3, right? So those many gigabytes of RAM that's available. And let's say your executor size, each of your executors, is, let's say, 32 gigabytes size, right? So how many executors will you be able to fit in 3 virtual machines? Anybody? So you have 64 gigabytes, 3 machines, and then 32 gigabytes per executor. How many executors can you have in the cluster? 6, right? Yeah. So 2 in each, basically, technically. But then you also have to account for some operating system-related memory, and you have to give a little bit. So you may not get 6 after all. So you may get 5. So let's say. So something to bear in mind that with that sort of executor size, you probably get that much parallelism. But then you can have, to start with 3, but then you have 10. So 32 gigabytes, how many in 10? So that is what it can scale up to, and scale down to finally, right, to 3. So that is what is possible. But then it doesn't mean that you have to allocate all those executors up front, right? So you can tell Spark that for this application, I just need, let's say, 2 executors, right, or 4 executors, so that it dynamically allocates within that available memory. And it goes, so let's say in this case I have 5, right? A possible 5. So it can go between 2 and 5. That is dynamic allocation of resources, of executors. So think about things like, you're running parallelly, you're running multiple applications, Spark applications. It's down to you to intelligently, smartly utilize what is available and be a bit frugal about it as well. So don't just put some random memory setting there, because it can affect other applications that are using your cluster. So it's just basically going through some of those things from an optimization perspective. These are important things to consider. And here on the right-hand side, these are session properties. So although your cluster has these settings on the left-hand side, the first screenshot, you can configure session-wise. In the sense, you may have a notebook which is running with, let's say, 5 gigabytes or 10 gigabytes data set, CSV file. But we have another colleague of yours who's sharing the same Spark pool who has a terabyte to scan. So you may want to just have a smaller executor, perhaps. And also, an important thing is this point here is smaller executors means more parallelism. So with the same existing cluster, with the small executor over here, you can have 19 executors. Whereas with the medium, you will have 9 executors. Any guesses why I may need a bigger executor? Yep.
Fit more things into memory.
Exactly, right? So if you're doing a very complicated join, let's say, right, and these things are happening in memory, so obviously you want more memory, so you want to have a bulkier looking executor. And if not, scale it down to small, and then you get more parallelism. Obviously, you get more 19 executors, right? So you can do more things in parallel. And the same thing, dynamically allocate executors. You can do it cluster-wide, as in pool-wide, Spark pool-wide, or just for your session, which is your notebook or your Spark application alone, right? So that's basically what this is all about. And yep.
So when you've got 3 nodes there, that's 3 executors, not 1 driver and 2 executors.
No, driver also would be part of that. Yeah, exactly. Yeah, good point. So you would have the driver and the executors within those 3 nodes. So something to bear in mind. But then, as it scales out, you just have 1 driver anyway. So you don't scale out the driver. So if it scales out because you need more executors.
But it does reduce the number.
Yes.
Of executors.
Exactly. Yeah, yeah. Good point. Now, the other thing which is important in Synapse is the intelligent cache, which is, any guesses what it might be? Okay. Yes. But more specifically, when you're reading data from the previous slide, I mentioned that you're ingesting data into, let's say, ADLS, right? ADLS Gen 2. So this is a network operation. So you're going to the ADLS storage, getting the data. You spend so much time actually bringing all that data into the cluster nodes because you want to execute some join or whatever in that cluster. You want that data to remain because the next query may reuse it, right? So you don't want to go back to the storage. So the intelligent cache will actually help you preserve some of that, or it's not persist, it's like cache for a certain duration. And that is something that is available, for you to play around with. But the important thing is, I also mentioned executor spills to disk whenever, let's say you've configured it to have a memory size of, what do we have here? A medium executor, 56 gigabyte. So let's say it's a very big join, it needs more than 56 gigabytes, then it spills to disk. So that all goes into the local storage where that executor is running, A. And B, there's also another thing I mentioned, which is the shuffle, right? The shuffles are also happening on the local disks, right? And thirdly, there is the cache. So you got to bear in mind that you should have enough local storage on that virtual machine if you want to implement the intelligent cache, right? So that's another important thing to consider. Okay, so what are Spark partitions? I covered this a little bit, but this is basically what happens. The statement below is just what it is. So Spark will split the data into smaller parts. So you can have your CSV files, let's say on ADLS Gen 2 somewhere, just point your Spark as that's the input, and then it knows how to split it into multiple executors. And each of those executors will be assigned a specific partition. And executors do map and reduce and everything. So it's like, it just picks up the task. No matter what the task is, it'll do it. What are Spark joins? So what are the different joins we have in Spark? There are 4 different joins. Probably 5, but 4 most important ones. Broadcast hash join is by far the fastest. That's because, I don't know if you can see the top green box over there. It's called the map side join. So again, going back to the previous slide here. So the map process here, map step over here. So those are mappers. So what will happen is when you're joining 2 tables, if let's say a fact and dimension table. Do you guys know about facts and dimensions? Yeah. So let's say you have a very small dim table. Yeah. So you want to join the fact and dimension table. So the dimension table can't fit into memory technically because you gave 56 gigabytes RAM, allocated that to the executor. You can bring that whole small table and put that into each of the executors. Yeah, so that you don't incur the shuffles and sort. So because the data is there, the entire table is there for the executor, it doesn't have to shuffle anything from another executor, right? So that works for a very small table. One of the table is very small. But if it's not that small, let's say, so there's a possibility that you have a bigger dimension table. In that case, it will not be able to fit into memory. Although I question why you have such a big dimension table. Well, leave that aside. But let's say you do have it. So then you can have each of those partitions of that dimension table brought into memory. And that is the shuffled hash join. no sort is required, but shuffling is required, right? And then there is the sort merge join, which is your traditional join, which is two big tables. Let's say you want to sort of go through that whole map and reduce step, map, combine, and reduce step, and then basically join the two tables. And last one is Cartesian. I don't think anybody should do Cartesian. It's just awful. Any database, warehouse, Spark included, it's just something you should never do. But then you can still do it. I don't know. I don't have a reason why anybody should do it anyway. So, all right. So let's take an example query. Nothing fancy. I don't know if you guys have seen the movie data sets on Kaggle. I'm not sure if you're familiar with it. Yeah, I've just picked it up. I just wrote a very simple, data ingestion sort of Spark notebook. Removed some of the nulls and called it metadata no null table. And then I have the ratings, which users have rated. And then all I'm doing there is just get the recent movies from 2020 onwards, and then get an average rating. And that's it. So anything that jumps out as maybe it can cause some bottlenecks. So what do you think in this will cause bottlenecks? Movie metadata is a sort of small table of, let's say, 50,000 rows or 100,000 rows. Not so many movies anyway. So, but still, what can cause problems from a performance point of view? If it weren't that small table, let's say they were decently sized two different tables, what do you think will cause? Yeah. I'm sorry, can you?
Both tables are going to have every movie in it, so the join is, the two tables will both be big.
Yeah, a join, yeah, exactly. So joins can cause some sort of problem, but more specifically, can you tell me what exactly within the join can cause problems?
One of the tables is small, so it wouldn't do the top one.
Yeah. So join, exactly, and then there is group by, right? So group by is also, you have to bring all of the data. Remember again, shuffling. So shuffling is by far the costliest operation within Spark, okay? So you got to watch out for that always. So if you have, I think I have a slide on that one. So yeah, well, so I have two tables here, movies on the left and ratings on the right. So ratings, obviously, there are several users who would have come and rated it, IMDb or whatever that is. So bigger table, that is a smaller table, right? And then what happens? I'll just go through the slides on what are the different steps that Spark will execute, yeah? So these are partitions, so this is split. So we have worker 1, 2, and 3, again, going back to that previous screenshot, so the 3 virtual machines. And you have the splits. So here you have worker 1 with these 2 keys, IDs. And again, going back to that example here, we're joining on the ID, right? So this is the movie ID, and then movie ID over here in the ratings one, right? So you can see the splits are basically, you can't really say where the keys would go, because it depends how your CSVs are and the cardinality of your tables and so on and so forth. So the splits can happen. So, I mean, it can be, all over, all the 3 nodes can have all the different keys, right? So in this case, you will see that 3 and 5 are here, 6 is here, 1 is here, and so on. So then what happens is that you got to bring all of those things into, within that worker, such that it can join Star Wars with this key here, so 1 to 1 here, and then compute the average, right? So that's basically what happens. So this is, now imagine 50, 100 terabyte tables, right? And the number of rows can run into trillions, right? Billions or trillions. So now think about doing this shuffling across these 3 nodes, how much of network latency there might be, right? So and with a higher cardinality table, and not many and many non-unique keys, let's say, so then it becomes even difficult a problem, and then with shuffling happening. So something to watch out. By default, there is this property at the bottom, so Spark SQL shuffle partitions. this is the property you can use to adjust your shuffle partitions, which basically means how many executors actually, how many partitions participate in the reduce process. So then you can basically limit it to the number of executors, a number of workers that you have, and by adjusting that, the network transfers will be reduced somewhat, A, but B, you probably have lesser parallelism. So you got to find that sweet spot to get to the shuffle partitions, such that you get the most optimal performance by scaling out. But at the same time, you will also, you should not incur, losses because of the latency, right? So that's something to bear in mind. But if you were on the latest Spark, I think, I don't know exact version of it, but 3.1, 3.0 or 3.1, I can look it up again, has something called as adaptive query execution, so AQE. And AQE is doing some of the shuffle partitions adjustments dynamically. So that is that's the next wave of innovation that's happening within the community. And Synapse already has that, so you can straight away move to 3.x version to get some of that performance enhancement. Cool. Right, quiz time. Broadcast joins are slower than sort merge joins. Yeah, it's false largely, but then something to bear in mind. So it might try, or if you've, OK, I didn't mention this earlier. So in Spark, you can actually give hints to say, hey, this particular table, you can maybe use it for a broadcast join. So you can give the engine some hints to say, OK, do this as broadcast, do this as sort merge, and so on. So you can provide that. I've not included that in the slides, but then it's there in the documentation. So you can go have a look, just search for Spark hints, for joins. You will see that page there, right? And I have that in the references, by the way. So if you want to have a look from the slides, you can straight go into that. So yes, it is false, although in some cases, if it has determined that it has to be broadcasted for some reason, it mostly won't, but it is a stress on the memory, obviously. So by the way, you can also adjust in Spark what is the threshold for participation, what is the threshold for broadcasting a certain table. So you can adjust that. So there is a default to say table size of, let's say, some X megabytes or a gigabyte. You would want it to be considered for broadcast. But then somebody might go and say, or reduce the executor size. So what will happen? You will have a lot of garbage collection and so on within your process. So that will not be ideal for broadcasting. So something to bear in mind. It depends, because the dimension tables or the smaller tables will be read into memory. So something to bear in mind. Don't reduce the executor size to something really small, such that broadcasts can't happen, or it can OM, etc. So something to bear in mind. But yes, really, it is what you said is right. So it is false. So we are at stop 3. Good. And how many of you are familiar from the database world? I'm saying that because we are in SQL bits. So many of you may be familiar with SQL warehousing, SQL Server warehouse. Yeah. OK. So yes. So when you're actually looking at the critical path of your application, so there are multiple stages that your application is going to execute this, right? So so the driver process initiates the whole thing. There are multiple executors that can participate in this. There are 4 in this example, in 4 different workers, and then those execute those stages in the query, right? Now, why did I say SQL Server? It's because there is the possibility of driver-only sort of tasks that are driver-only in the sense they're single-threaded, like I said. And then there is also the skew. So I don't know if you guys are familiar with data skew. Yeah. So when you're running the partitions, so let's say you're performing the reduce step. OK. So the reduce step, and I think I have a slide on this one. So let's go. Yeah. In the reduce step, let's say the particular key that you are, let's say, doing a group by on, or that column, basically, sorry. One of the keys is like, it has plenty of, rows that correspond to that particular value, right? So in this particular case, number 6 over there is there is a skew there. So you can run queries like what I have given. This is a simple Scala or Python code that you could write, where you say just data frame is basically an in-memory representation of, let's say, your CSV. So you read in the CSV, get a data frame, and then you can sample it to say, get me a percentage of the data, and group by a certain key, which you suspect has a skew, right? And then get a count, and then sort descending. So you will know from the sample, if it is representative sample, then obviously you will know that a certain key is sort of skew. So this is not something that, I think you guys are familiar with it. If you're coming from the data warehousing background, it's very similar. And then there is the Spark UI as well. So why I put that is because how do you, what happens in Spark is that you're running a certain query. The example that I gave, you could be running something like that. What happens is it completes, and going back to this previous slide, it will say that 90% or 99% of all the tasks have completed, but one is just stuck, right? So 1%, it doesn't advance to 100%. And you'll be like so happy when your query started to run, right? So you're like, oh, brilliant, it's going fast, and then it goes to 99%, and it's stuck, right? So, and then you start to worry what exactly is happening, right? So the most important thing that for you to consider there is to go to Spark. The most important thing to do then is to go to Spark UI, which is there in the notebook, by the way. So you can just go click on the Spark UI, and then you will see the execution graph. You would see when were the executors added, and then you will see the different stages and blah, 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 all of that. And then you go to the task that is taking so much time, right? And then when you click there, you would perhaps see that task number 1, in this case, is queued. And then you'd say, OK, this is not working, so maybe you'll have to go and change the data, do some salting or rebalancing and so on. There's a hint over there that I've provided in the bullets below. So you could run some rebalancing. You could provide some rebalance hints to Spark Engine. There's something called a skew join optimization. Maybe you can enable that, and so on. So, and then you can also change your data sets such that it is more distributed. So use certain keys or a set of keys such that you can probably add a column as well to your data such that the distribution can happen more evenly across all your workers. So in the references section, there are some links I've provided which will help you with dealing with data skew, basically, right? So this is an important aspect that this is an important thing that can contribute to performance problems, right? So the last section I have is on the data formats, tables, files, and storage. So typically, what we have seen is with Spark, sometimes what happens is people just get a dump of CSV files and they start analyzing it, and they'll figure that, oh, this is not really efficient. Has anyone faced this problem where you have used something like a CSV file or a JSON file and read the data into Spark, and then you notice that it is slower? Why is that happening? Any guesses? Anybody has experienced it? Yep.
Run a single thread?
No, not really. No. Anyone else? OK. So with binary columnar formats, are you familiar with columnar formats? Yeah. OK. So Parquet, ORC, etc. You're able to select. If let's say your query is select movie ID and movie title. OK. So it is able to select just that column, read that column into memory. Whereas with a CSV or a JSON, you have to read the entire row. Now think about it like you have a very wide table with, let's say, I don't know, 500 columns or something. Then it has to go row by row and read the whole thing. So then there is a cost on the memory, obviously. So how much the executors have to, how big the executors have to be to accommodate that entire table in memory. So, and as we have seen, if the executor becomes big, what happens? Parallelism reduces, right? Obviously. So it's always good to have columnar formats and binary formats and compressed with snappy compression. We've seen that Spark is very efficient in dealing with Parquet and snappy. So that's something that you want to probably convert as soon as you get your CSV files. So something to bear in mind from a data format point of view, create tables with Parquet and snappy compressed data. I have deliberately not gone into Delta in this session because Delta is V2 of this talk, and it will need 50 more minutes. So, but Delta is supported, suffice to say, I think. And some of my colleagues actually even, I don't know how many of you have attended my colleague Mike Dobing's talk this morning, who talked about, lakehouse architecture. So he did go into some details of Delta over there. But Synapse supports Delta for upserts and deletes. Just having Parquet is not enough. So it's not a traditional data warehouse like platform. So Spark alone can't help with upserts and deletes. You have to have Delta formatted tables in order to have that capability. Watch out for small files. And any examples you can think of how small files can come in your data lake? Anybody wants to take a guess? Absolutely, stream is a very good example. So think about things like events that are happening every minute, and then there is a certain payload that your machine, it could be an IoT device, whatever, is sending some sort of event that this happened, and that is coming through the stream. Event hubs, maybe in Azure, and then your Spark application is reading that into a data frame and then writing it, or Event Hub Capture is capturing it into a data lake as small files, right? So if that happens, then I'm not saying it won't work, but then it is a performance inhibitor, right? So something to bear in mind, when you have millions and millions of small files, Spark will underperform. So it's always good to collate it into something like maybe 128 MB to 256 MB Parquet files, snappy compressed. That's usually a good sweet spot from a file size perspective. And wherever possible, just use Data Lake Gen 2 storage premium. It's always good for that, and for faster listing and renames. Any guesses on where are we doing listing in this whole operation? So you remember that slide in the beginning? This one? So there's input and splits. So split computation happens when you're listing the files. Like, what are the different files I have to process, right? So the listing happens in the very beginning. And traditional blob storage is not a file system, right? Blob storage is a set of blob files without a directory structure or a folder structure. So ADLS, Gen 2, and Premium especially will provide you with that capability like it's a file system. So the renames and listing is much faster. I wouldn't say it is as good as a local file system, like a Linux file system. It's not as good as that, but still then it is much better than having a blob container, okay? So again, from a tables perspective, it is good to use ADLS Gen 2 and Premium, right? I think it'll be like, it's probably needless to say, I think it's obvious to people here, everybody familiar with analytics and data warehousing, always partition your tables, right? So date partition, region partition, and so on. Obviously, it'll help your queries. Can't emphasize that enough. So I have seen customers dump all their CSVs into one single folder and then wondering why exactly is it not performing very well. And obviously, you gotta have your year, month, day, whatever, storage partitions as well. Not just the in-memory partitions of Spark, also have a good table structure with partition by clause. Spark in recent times also has bucketing support. So there might be situations where your tables can't be partitioned, for some reason. Maybe you want to use bucketing in such cases. So bucketing is basically, you can have a fixed number of buckets predefined. Then you can say the various, the data has to be, the input data has to be split across these buckets. So it works similarly like partitions, but it's not as well. So okay, so last slide is on Microsoft innovation. So Microsoft, we have also implemented what is called as hyperspace. So it's a very new area of indexing Spark and big data workloads, so for providing query acceleration. So it's an open source contribution from Microsoft. It's an, as I said, indexing subsystem. And it will allow, I think now I can see in the documentation that there is the Parquet support as well. So you can use Parquet and hyperspace on top of it, and that will help with the query acceleration. So something to play around, and it is open source as well. So it's good. So it's a brand new thing. So something to explore. And this is the last quiz. Ooh, sorry. Avro, we didn't touch upon this. So the last question is slightly more difficult. Avro is a binary data format, true or false? Come on, we have to get Sonic to the goal, right? Yeah? It's not?
I don't know a lot about it. I think it's false.
Anybody else thinks it's true? Yeah, he's right. Just playing with you. All right, so Sonic, yeah, he's very happy. All right, so as I said, I have references and further reading over here. And yeah, open to questions now, and I'll, yep. Sorry. It is not. False is right, yeah. Yeah, and I have, this is my email address and LinkedIn and Twitter link to my profile, and the feedback link as well. So please do provide your feedback, and yeah, and these slides I think will be there with you guys in, I don't know, just after this, I don't know, after the SQL bits, I think. So yeah, any questions?
Sort of way to view real-time performance of Spark, kind of like Ganglia.
Yes, Ganglia is a good tool for monitoring. Yeah, certainly. I mean, you can use that. Yeah, definitely. Yeah. Yeah, it's 128 MB, 256 MB per file. Yeah. Yeah, you can also go up to maybe even a gigabyte. Then I would probably, maybe half a gigabyte, maybe 512 as well. So, but 256 to 500 is usually really good. All right. Yeah, I will be around, as I said. So if you have questions later, yeah, please feel free to, yeah.
So just one came in remotely.
Yes, please.
How is the cost compared to Databricks?
I'll tell you what. So cost is very interesting. So the cost of the cluster is usually way higher if you have really big data, right? So if you're in the ballpark of somewhere around 10 to 50 terabytes, 60 terabytes, you'll probably be exploring other technologies as well, including the serverless SQL in Synapse, isn't it? So anything bigger than that, and also if you want the delta and all the goodness of delta and so on, then obviously Spark is a good alternative. So there are two elements to Databricks pricing. One is the DBU, which is the Databricks unit, I think it's called, Databricks unit. So the more the number of nodes, more the DBU, right? So if you have a 100 node cluster running for X number of hours in a month, you'd have certain DBU for Databricks that you'll have to pay additionally than apart from the VM cost, as in the executors where they run, etc. So that is one additional pricing element or a factor. In Synapse, you'll probably not have that. Yeah. Yep. Any other questions? Remote? No? All good? Yeah. Okay. Cool. All right. That's it. Thank you very much, everybody. Thanks for coming. And yeah.